Imagine one day you're working in a computer store, then a customer comes in, picks up a 1.5 terabyte external hard disk, then asks you, "Excuse me, sir, how many bytes are there in this hard disk?" You're probably going to look at him quizzically and say, 1.5 terabytes? No, that's not what I'm asking. What I'm asking is how many bytes are there? So you take a step back, you think about it, that maybe he's asking for how many gigabytes there are. So you answer, alright, it's about 1,500 gigabytes. Oh no, I don't want to know that. I want to know how many bytes are there. You are taken aback by the question, but as a good salesperson, you will still answer that fellow. So you take a step back, you start to count the number of zeros, and then finally you answer him. 1,500,000,000,000 bytes. Well, you should be glad I'm not the customer, because if I were the customer, I'll be asking, if I had 1,000 of these hard disks, how many bytes are there? Can you write it down for me? It is probably going to be very frustrating to count the number of zeros accurately and then to tell that person. Well, guess what? That's what the scientists have to struggle with. They have to struggle with very, very huge numbers and very, very small numbers. Very large numbers like, what's the distance between the Earth and the Sun? Very small numbers like, what is the weight of a dust particle? That is where they came up with the standard index form. Standard index form is a type of number system that represents very huge numbers and very small numbers into this, where this is called the coefficient, 10 is the base, and this small number here is the exponent. Now, because of this, there isn't a need to manually write out every single zero in the numbers, for the base and the exponent will take care of that. Here's learning goal 1, how to convert numbers into standard form. Step 1, put the decimal point after the first digit and drop the non-significant zeros to get the coefficient. The coefficient has to be at least 1 and strictly less than 10. Step 2, count the number of places from the decimal point to the end of the original number to get the exponent of the base 10. If the number was a very, very small number, then we put the decimal point of the first non-zero digit to get the coefficient. Likewise, the coefficient has to be at least 1, but less than 10. Then we count the number of places between the new decimal point and the original decimal point. The exponent of the base 10 is a negative value of this number. This brings us to learning goal 2. How can we tell when the exponent is positive or negative? Let us first take a look at a very large number. In a very large number, we will need to shift the decimal point from the ones placeholders to the tens, hundreds, thousands, so on and so forth. With this, we are moving up the placeholders. As we're moving up the placeholders, the exponent is positive. As for very small numbers, we are moving the decimal point from the ones placeholder to the tenths, hundredths, thousandths, so on and so forth. With this, we are moving down the placeholders. And because we're moving down the placeholders, the exponent is negative. This marks the end of this lesson. But before we go, here are some practice questions to check your understanding.